So let's continue and add to this concept of western boundary intensification, right? So let's assume that Earth was not a sphere and instead was a cylinder, right? What does that do? Basically, the rotation axis then produces the same distance to every local point on Earth, so the Coriolis doesn't change. I hope it's very obvious why Coriolis increases with latitude. Basically, the axis of rotation is going through from pole to pole, and the latitudinal circle is smaller and smaller as you go towards the poles from the equator, right? So if you draw the local radius from the center of the axis to the surface, it's smaller and smaller as you go towards the pole from the equator, and you are rotating with respect to that latitudinal radius. So that's why you have increasing Coriolis. So if you have constant Coriolis, which is typically represented by factor F, then you will have pressure gradient, force, and Coriolis directions occurring this way, and you will have no asymmetry because the Coriolis is constant. You can change the Coriolis and change the shape of the gyre. So for example, Earth is rotating at 24 hours for one rotation. Mars is almost the same, whereas Venus is almost 117 Earth days for one rotation around its axis. So Coriolis is not the same on all planets on the solar system, obviously. So if you just imagine for some reason we increased or decreased the Coriolis, then you can, but kept it constant as a cylinder, you can squeeze it, right? And here's a cartoon of showing why the middle of the gyre, the thermocline is pushed down and sea level goes up. So you are taking near surface warm water and converging it. Water cannot go up, so it has to go down. That's why we call it downwelling or convergence. If you push warm water down, it's going to push the thermocline down, and you can think of it as larger volume of warm water, so it occupies more space and the sea level goes up. By the same token, we have something called upwelling, where water diverges away from a point, cold water comes up from below, thermocline gets shallower, water is denser, and then sea level goes down. So going back to what we are trying to do with the western boundary intensification, basically, as we said, wind is moving water south, so we have to move the water back north to prevent constant southward flow onto the equator. Mass balance is needed, and we said wind is putting in negative vorticity, so we have to generate positive vorticity somehow to prevent the ocean from spinning faster and faster and faster, so we have to also balance vorticity. So where can we move water north and produce positive vorticity? Right? So here is the gyre with its asymmetry. There is this broad southward flow shown with red arrows. If the flow is on the west, you're moving a lot of water south in the broad gyre. You have to move it north in a very small space, so you will have faster, deeper, stronger current. And the other way is that you move the water north on the eastern boundary. So you're moving water south in blue arrows here, and the gyre is asymmetric with narrower, stronger, deeper current on the eastern boundary. Which one of this will satisfy the other condition? Both of these are moving water north, but where would you generate positive vorticity? You can understand that by looking at these schematics of the figure. So let's imagine that the red line here is the east coast of the US, and it's the Gulf Stream. Imagine it like a frictional current, so on the boundary you have very small velocities or zero velocities, and the velocity has to match the gyre as you go interior. So you have increasing velocity. What is the direction of vorticity in this case? You again have to curl your finger towards the rotation that will be created. So if you imagine you put a paddle in the middle of this Gulf Stream, which way would it rotate? If currents are faster on this side and slower on this side, it's going to rotate counterclockwise. You curl your fingers, you get your thumb going up from the surface towards the sky. That's the positive Z or Z direction, so you have positive verticity being generated. Whereas if you have a narrow frictional strong current on the east, let's say this is the coast of Africa and Europe, then you have vorticity again going into the ocean, so it's negative, so it would just add to the negative vorticity by the winds, and it wouldn't balance vorticity. So the only way to balance vorticity on a sphere with Coriolis changing with latitude and move water north because of trade winds and westerlies is to have the western boundary current, strong, narrow, deep western boundary current on the west coast. This is how you end up getting western boundary intensification. This was not known before the 1940s. A very bright young scientist who then did amazing work for decades at the Woodsole Institute of Oceanography. He was at Harvard and then MIT at Woodsole and so on. He was the first one to show that it is the change of Coriolis with latitude, which is called the beta effect. Beta is the gradient of Coriolis in the y direction. So it is this beta effect that causes western boundary intensification. Amazing discovery. You can imagine when he first discovered this, how amazing it was. Okay, now you must learn the processes of how this works. So here this is showing the interior flow and the frictional boundary flow and how we match the negative vorticity of the winds with the positive vorticity of the frictional boundary current. Mathematically doing this is not so difficult, but you have to go through some complex math, but nonetheless in a dynamics course I will teach that part. The interior flow is called a Sverdrup flow, which is driven by this vorticity or the wind stress curl as it is called, and we will see that in another context later on. Okay, so there are some classical works by Monk and Veronis and Stommel and so on which show how this works, whether it's the bottom boundary friction or the side boundary friction that is needed, etc. So the eastern boundary doesn't work. You can satisfy mass transport but not the vorticity constraint. Okay, so western intensification then is frictional forcing by the winds of the surface causes a pile of water which causes geostrophic velocity and southward transport because Coriolis increases. You need to satisfy mass balance, so move water north, and vorticity balance, so you need a western boundary current that is narrow and deep and strong compared to the eastern boundary current, which is very shallow, much broader, and carries cold water because it's going from higher latitudes to lower latitudes. So typically all the fisheries, rich nutrients, primary production is all on the eastern boundary, as we will see later on when we do biology. So you just learned one of the most important concepts, actually two of them, geostrophic currents, geostrophic balance, and western boundary currents. Please go through them, make sure you understand them because they are critical.